as I said, we are going to review the chapter 1 to 3. So some important concepts. Pretty much I'm going to take some problems. We're going to work on the problems together. Okay. The first problem, we're going to illustrate the concept of conditional probability and independence. So problem 1, if we have a fair coin tossed repeatedly, show that with respect to time, a head turns up sooner or later. We need to prove that. A fair coin is tossed repeatedly. Show that how to prove that a head turns up sooner or later. So what kind of concept are we going to use in this proof? So we're going to, first, with respect to time, what is this? This is limiting, right? Limiting solution. And how to prove this is we are going to use the complement. An event is going to happen equals to 1 minus probability, the complement of the event. So probability, let's see if there is a no head forever. What is this probability? This will equals to the limit n goes to infinity probability no head in the first n tosses. What is this probability? This will equals to limit n goes to infinity 1 over 2n. Okay, because first n tosses, each one is one half. You have to multiply all of them together, and this is 2 power n. Now n goes to infinity, 1 over 2 power n, and you have a very big number, 2 power n in the denominator. So what this will be? This will goes to 0, right? So probability a head shows up eventually. It's actually 1 minus probability no head ever. So that's why this is actually 1. Sooner or later, it's going to come up. Okay, next we're going to talk about what is independent. We keep talking about we have independent trials, and how to formally define independence. So if we have two events, event A and event B, if we're going to say event B is independent of event A, so only if probability B given A equals to probability B, okay? So this is a definition of independence. So event B is independent of event A if this is true. Okay? Okay. Now, suppose B is independent of A. Now the question is A also independent of B? So now we're going to check this problem. Okay. I think after I switch. So probability A given B. Why is it but this is not the line width I want? Let me change it. Okay, so this will equals to probability B given A times probability A divided by probability B, because you have the PAB. This is actually equals to But here we are saying B is independent of A. So this will equals to probability B times probability A divided by probability B. So this will equals to probability A. Okay. So the answer is yes. The independence is symmetric. A symmetric way to write this is probability A intersects B equals to probability A times probability B. So independence is a symmetric pairwise relationship. Okay, now let's look at a new problem. Pairwise and mutual independence. Okay. Let's read this problem together. A fair coin is tossed twice. That A is the event that a head shows in the first toss, and B is the event that a head shows in the second toss. Okay. Now you have two toss. Toss 1, toss 2, and a head shows up. Now C is the event that the total number of heads in both tosses are even. Okay. Number of heads in both tosses are even. So even means you only have two tosses. Even means either 0 or 2. Now the first question is A and B are independent. Why? Why? Because you toss the head shows up in the first toss and the second toss, they are independent trials. Now let's see if we have toss 1 and 2, and then we have probability, right? If toss 1 is head, toss 2 is head, what is this probability? How many possibilities we can have? You have two tosses only. 4, 2 by 2. So this is head head and head tail, and then you have tail head and tail tail. And what is the probability for each? 1 over 4, 1 over 4, 1 over 4, 1 over 4. So add them together, all 4 events. They are just 1, right? That's all the possibility I can have. Now second, let's calculate what's probability of A. What's the probability of A? A head shows up in the first toss. 1 over 4? 1 over 2, yes. And what's the probability B? The head shows in the second toss. Now we only talk about the second toss. We are not considering head or tail show up in the first one. We're just saying, oh, head shows in the second toss. What's the probability? It's the second toss. And the second toss, you only have two possibilities, head or tail. And the head shows up in the second toss is actually 1/2. Okay. Now, so we got probability A and probability B. So what's the probability C given A? So what is C? C is the total number of heads in both tosses are even. Okay. So if we translate this, this is a probability number of heads in both trials are even. too far. Let me put it over here. Given, yes, given that the first toss is head, so this is the probability. Okay. So number of heads in both trials are even. Okay. So what is the number of heads in both trials are even? Here. Huh? Oh, this one. I have another one. Here. C is number of heads in both trials are even. Okay. Given that the first toss is a head. Given that the first toss is head, and both of them are even, right? So what's the probability of, given that the first one is head? 1/2, right? And this equals to probability, actually, B. So probability C given A is actually equals to probability C, because probability C is actually equals to probability HH plus probability tail. This equals to 1/2. Probability C is both of them are number of heads are even. So either it's head or tail. Okay. So A and C are pairwise independent. Similarly, B and C are pairwise independent. Now, the last problem. If we have probability C given A and B, so probability if the first is the head and the second is the head, what is the probability of C to happen? Given that the first toss is head, second toss is head, what's the probability that it's even? It's 1, because it's 100%. If given that this happens and this happens, it's 1. But this does not equals to probability C. This is 1/2. So that's why they are not mutually independent. Okay. So independence of events definition. So here is a definition, formal definition. If you want to check, instead of just heuristically you think, oh, they are independent, you just check this probability, whether it's true. If this is true, they are independent. If they're not true, they are not independent. These two, they are actually the same. Now, I have a question. Is disjoint equivalent to independent? So you have two events. This is the whole set. Okay. Now you have A here. You have B happening here. This is your space, event space. And you have A and B. They are disjoint. Whether this is equal, are they independent too? So let's think about it. If two events are disjoint, then the probability that both occurring is disjoint. A and B, no intersection. So both occurring at the same time what is this probability? Yes, 0. So what we have is PA join B as actually equals to 0. But here we have A happening over here. Probability A happening does not equals to 0. Probability B does not equals to 0. So over here, if we have PA intersects B, does it equals to PA times PB? That's not equal to. So that's why disjoint does not indicate independence. Disjoint just mutually exclusive. Okay, now we finish this problem. Let's move to the next one. A and B are independent events. Show that A complement and B complement are independent. Okay. So A and B are independent. Now the question is A complement and B complement are independent too? Okay. So suppose this is AB. Have it over here. This is A, this is B, and this is what is happening right now. Okay. Now let's first consider A and B complement. Okay. So probability A join B complement. So what is A join B complement? B complement is actually everything outside. Okay. Now A intersect with everything outside of B. What is the area? Right here, right? Yes, excellent. So this is actually probability A does not include the intersection of A join B. Is that right? That's what you're saying, right? So this will equals to probability A minus probability A join B. So, but we know that probability A join B, they are independent. So here is a condition, they are independent. So this will equals to minus PA times PB. So this will equals to probability A times actually 1 minus probability B. This will actually equals to probability A times probability B complement. So to this point, we can have a conclusion that A and B complement are independent. So in other words, A and B independent. So we can have A and B complement. Huh?
A complement. Sorry.
What? It's B complement, right? Okay. Are independent. So if we are using the same logic, now let's replace So suppose A is BC and A are independent. By the same logic, then we can have A, B complement, and A complement are independent. This is the logic is like this. You see, this is A and a B. So if we replace B as B complement, they are still independent, right? Now, if we have B complement and A are independent, now this is actually independent. We have already proved. Now, if we just put it over here, and because A and B are independent, so if we just replace B with a complement, they are still independent. Now, B complement and A independent. Then over here, if we replace A with A complement, they're still independent. Okay, that is the same logic. This is the same logic. We have this. So up to this point, we have BC and AC are independent. Am I making sense? Okay, if an event A is independent of itself, what is the probability of A? So this is a new problem. So let's just use the definition. If the event is independent of itself, find probability of A. So A join A should equals to probability A times probability A. That means probability A join A is probability A. Is actually equals to probability A squared. Now this problem is asking you, what is probability A? Solve this problem. However, probability A should be less than or 1 or greater than or equal to 0, right? So what is probability of A? Huh? Yeah, 0 or 1. So this problem is done. Now consider event A and B. Now we have a third event, C. Okay. Now what if probability A given C greater than probability B given C? And probability A given C complement greater than probability B given C complement. So what is the relationship? What can you say about this A and B? So what can we say is, are they greater than or are probability A greater than B or equal to or less than? Can you tell me which one is bigger? Just based on the condition we were given. So in order to solve this problem, let's do the total probability rule. That is probability A given C times probability C plus probability A given C complement times probability C complement. What is this? This is the total probability rule. So I hope this review actually refresh your memory about total probability rule, conditional probability, and those and the complement that we have studied before. So based on this total probability rule, we have this relationship, right? This relationship right here, right here. Let's just replace it. Let's put this one here, this one here. So this will equals, this will greater than. This will be greater than probability B given C times probability C, okay? And plus probability B given C complement times probability C complement. And what is this? This is probability of B. Yes, excellent. So what we have is probability A greater than, the relationship is greater than probability B.